Hey everyone, thanks for joining my talk. And my name is Adam Andrews, and I'm a PhD student at Stockholm University. In this talk, I would like to describe a method that I've developed, which with we can constrain primordial non-Gaussianity in galaxy redshift surveys. Now, primordial non-Gaussianity is an essential probe that we have to our disposal to constrain primordial universe physics, which is one of the key tasks of next generation of space missions. And after this talk, I hope to convince you that my method provides a unique opportunity to maximally extract the information that is available in these surveys to constrain primordial non-Gaussianity. So to give a little bit more of a background, what we're interested in answering is the number of fields which are active during cosmic inflation. Cosmic inflation being the canonical model to generate the primordial seeds of the universe from which the large-scale structure grew into existence. The standard model kind of predicts that we would have a Gaussian-like initial conditions, but we can introduce this primordial non-Gaussianity as a form of, to the simplest order, as a form of a Taylor expansion of the primordial gravitational potential with this nonlinearity parameter FNL. Now, if we would be able to detect or determine that FNL is non-zero, this would indicate that there were multiple fields that were active during this initial era of accelerated expansion, the primordial universe. So to head over to the observational status, kind of try to summarize it in this image here, where the strongest constraint on FNL comes from the cosmic microwave background, which constrains FNL on the order of ±5. However, cosmic microwave background is not expected to yield any stronger constraints on FNL by itself, since the largest scales have already been probed by Planck. So instead, we're turning our attention to next generation of galaxy redshift surveys, which probe the three-dimensional information in the cosmic field. And the goal of these next generation galaxy redshift surveys is to bring down the uncertainty on FNL down to order of ±1. And this links back to the question of finding a non-zero value of FNL. So currently, this has been done for existing data sets, the SDSS data sets, where we find with a combination of power spectrum or bispectrum estimators, FNL under order of ±20 or 30-ish, basically. So in this method I developed, I wanted to try to go beyond these summary statistics that are available to us right now, and instead kind of utilize more of the cosmic fields. And to give a little bit more motivation of this, I would like to have made this animation which kind of illustrates how the cosmic field is affected by this FNL parameter. So on the left-hand side, we have the initial density field, which when perturbed with the FNL parameter becomes, of course, highly non-Gaussian. The effect that this has on the middle panel, the final or present-day dark matter field that we have around us in the universe, we see that these underdense regions become smoothed out, while these peaks become even more sharpened and raised as an effect. The effect that this has on the galaxy field on the right-hand side is that this introduces a scale-dependent bias effect, meaning that the galaxies kind of leave these under-dense regions and travel instead to these over-dense gravitationally regions as an effect, direct effect of FNL. So what I'm interested here is that I want to use all of this phenomenology, this rich phenomenology, and go beyond summary statistics. So to do so, I want to fit the full cosmic field directly to the data. And to do this, I'm working in the framework of field level inference. To give an intuitive understanding of field level inference, I usually think of it as a combination of a forward model, or of two components really, a forward model and a statistical inference approach. The forward model allows us for any set of initial conditions and model parameters make a prediction on the final or observable state of the universe, meaning that we have a set of galaxies that we can observe. So by introducing this physics model or this forward model, the question becomes really of which set of initial conditions and model parameters were used to generate this final observable galaxy fields. So what we have to do next then is to utilize statistical inference approaches, Markov chain Monte Carlo mainly, to sample through plausible values of the posterior distributions, which could have given rise to these observations. So we mathematically write down the posterior and put that into our statistical framework that we have dubbed Borg, Bayesian origin reconstruction of galaxies. And Borg works similarly as how one would expect that we could draw samples from a two-dimensional posterior distribution. So by exploring through possible values of the posterior distribution, Borg is able to generate samples, plausible samples of the initial conditions and corresponding model parameters, which could have given rise to observations. Of course, we're not working in a two-dimensional framework as is here, but we're working in a very high dimensional, very complex dimensional space, posterior space, which lies on the order of 10 to 100 million different dimensions or parameters, corresponding to the density value of voxels or the cosmological parameters and other nuisance and hyperparameters, basically. The benefits of this approach are a couple. Mainly, we're able to go beyond summary statistics since we don't break down or kind of simplify the field anywhere. We're using the entire field, cosmic field, in our analysis pipeline. We're able to include higher order correlation functions in or higher order statistics in the density fields. Since we're using this forward model approach also, we're able to handle observational effects or survey systematics in the analysis pipeline itself instead of handling or post-processing of the data, for instance, to mitigate these effects. We can handle this in the analysis pipeline itself. On the question of primordial non-Gaussianity, what's important for us here is that we're able to utilize multiple probes or multiple effects that one could use to constrain primordial non-Gaussianity. I've talked about the scale-dependent bias, which is an effect in the power spectrum, galaxy power spectrum. And of course, we also have small-scale effects, which can be measured by the bias spectrum, but we also have other effects which is sensitive to primordial non-Gaussianity, for instance, peculiar velocities and mass distributions, skewness and kurtosis of the density fields, etc., etc. And this is all gathered into one single pipeline, analysis pipeline, basically. So some plots later about how we can infer the initial conditions, but I'd like to go on to the next part of the talk and try to keep this method description leave this method description for now. I'm happy to answer questions later if you have any questions on the method itself. There's also this webpage where you can read more about Borg, which is this hierarchical framework we use to conduct our Markov chain Monte Carlos. So there's more description on that there, but there's also other projects that we've made with Borg. So after we've developed this physics model, this method, we wanted to, of course, apply it to demonstrate it with a proof of concept, which we have done in the paper. So in the paper, we generated from the SDSS 3 galaxies redshift survey. We wanted to generate our own set of mock data so we can have control of the initial conditions and can include a primordial non-Gaussianity in there as well. So from the SDSS3 dataset, we emulate or extract features which are essential or which are linked to the SDSS3 catalog, such as radial selection functions, sky coverage, survey volumes, number statistics, galaxy number statistics, etc., etc. And we include also primordial non-Gaussianity, and we simulate then our own mock data, which emulates basically key features of this SDSS3 redshift survey. After that, we apply our method. We run this Markov chain Monte Carlo on it, and we have some then results that we present in the paper. So I would like to highlight some of these results now here. First and foremost is kind of the robustness of the method. It's something I mentioned earlier, that we can handle survey systematic effects. What we do is that we, throughout this Markov chain Monte Carlo, we can simultaneously handle bias values and marginalize out bias values while we also can sample FNL parameter. So just to show this, it's not very legible here, the corner plot, but it can be found in the paper itself. But what this kind of demonstrates is the robustness of our method. We're able to handle unknown linear bias effects, and other bias effects from the galaxy bias relationship, together with also survey effects such as the window selection function or other contaminations which could exist in the data. Next, I want to go over to the inferred density field, which is a unique or a side product that our method generates. So basically, for any set of any set of observations, any set of mock data in this sense, or in this setting, we can infer plausible density field realizations, which is connected to this mock galaxy data. Basically the underlying density fields. With this ensemble, we can then estimate expected underlying density field realization, is exemplified by the middle plot here, where we can also see the effect of the window function, of where we have observations, we have stronger statements on the underlying density field, while where we don't have any observations, where the kind of regions that are masked out in the universe, we see that the standard prediction results into the cosmic mean, basically. And similarly, as we have a mean expected value, we also have an uncertainty or a variance on these values, on these density fluctuations. Which, of course, again, here shows that where we have observations, we kind of have even smaller uncertainties on the observations, and where we don't have any observations, again, we have this cosmic mean realization. These density fields or these inferred initial conditions can be used to run other projects or to do other explorations of the primordial universe, or be used in, for instance, in constrained simulations. Of course, the main results of the paper is how we can constrain FNL. And for a kind of a high resolution SDSS3 galaxy redshift survey, we can constrain down to FNL of ±9. And just to reiterate, this distribution constitutes a full statement on the information content available in the data, since we're able to fit the cosmic field a voxel by voxel level and with model parameters as well. Compared to other measurements on the SDSS3, on similar measurements, we find that other researchers have been able to find ±29 on a similar data set, basically. So the next steps for us really is to of course improve the algorithm even more. I mentioned earlier that this ensemble or this posterior distribution was the result of a higher resolution. We've also been running with a kind of a lower resolution in order to see the effect that resolution has on the final data product, basically. Also in the paper, we made a mock data which emulates typical features of a stage 4 survey, Euclid, Vera-Rubin Observatory, or SphereX, and use this as well in an analysis task. And we find that we're able to also successfully constrain FNL for this kind of surveys for 2 different resolutions as well. And again, you can see that we kind of have this dependency on the resolution that we utilize. But not only is the resolution a factor of how well we can constrain FNL in here, or how the scale that we can resolve affects FNL, but that we also see that with further tests, we can improve the FNL constraining power by changing the forward model. Specifically, we can alternate or increase the structure formation model by going from a Lagrange perturbation theory. We hope to be able to make stronger constraints by using a second order Lagrange perturbation theory or an n-body solver, such as a particle mesh method. We're also looking into ways to upgrade, to optimize the physics model, or to better improve the physics model, and more specifically, the scale-dependent bias model that we've used here previously. Of course, we're also working diligently to prepare for other stage 4 surveys, since this is the big reason why these missions have been sent out or have been started, is to constrain primordial non-Gaussianity. We wish to apply our method to those papers as well. So we're trying to improve the efficiency, being able to use large volumes or large scale volumes while simultaneously maintaining the resolving power of said data. So to bring this all back in a quick summary, this method that I developed constitutes the first field level inference of primordial non-Gaussianity, and we've been able to constrain FNL to ±9 roughly on SDSS3-like data. Hope to bring this further down in the future, but mostly we'll be focused on next generation of galaxy redshift surveys most primarily. With this method, not only can we handle survey effects such as the window selection function and other contaminations in the data, we're also able to handle higher order statistics, and we can handle it in this robust fashion by also sampling nuisance parameters and marginalizing them out in the analysis. Additional data products include the inferred density fields, which can be used in other research projects, for instance, and also it's a nice side product basically of this method. Thanks for tuning in.